Our next is to try and compute soil constituents, where we are given certain parameters and being asked to calculate the rest. So a sample of saturated clay was placed in a container. So saturated clay. So note, saturated clay is a keyword you should take note of. Was placed in a container and weighed. The weight was this, 6 newtons. And then the clay in the container was placed in an oven for 24 hours at a certain temperature. The weight reduced to a constant value of this. It means the value did not change again after it was placed inside the oven. And so we have this. The weight of the container is given as 1 Newton. So if specific gravity is 2.7, determine the water content in that sample, the void ratio of the sample, the bulk unit weight of the sample, and then the dry unit weight of the sample. And finally, effective unit weight of the sample. So now we know the weight of the sample plus the container is 6 newtons. So after the sample was dried, the new weight became this, including the container. So if we know the weight of water, we want to determine the weight of water and that of the dry soil. So now if I know that the sample weight of water can be determined, since we still have the container, so we are assuming the container is not taken out. And so I have that of the 6 minus after it was dried, giving me 1. So the weight of the water is 1 Newton. And the weight of the dry soil itself, remember they said the weight of the container is 1 Newton too. So you subtract the weight of the container 1 to get the weight of the soil. So determine the water content. We know that weight of the water, which we know as 1, over the weight of the solids, which we know as 4. And so expressing that as a percentage for water content, I have 25%. Then determine the void ratio. Again, we go for that our beautiful formula, which looks like this. We go for that formula and make E the subject of that expression. And so in that expression, they said our sample was saturated. I kept emphasizing on that, saturated. So saturated, since the sample was saturated, we have S to be 1, which means the degree of saturation was 100%. And then you know your water content as 25% from here, and you know the specific gravity was given to you as 2.7. So your void ratio can be computed to be 0.675. Note that the denominator is the weight of the solids, not the total weight. So they are referring to this. So when you are checking the weight of or water content, we use the weight of the solids and not the weight of the entire sample. Then our next phase is for us to determine the bulk unit weight. So bulk unit weight, we usually will make use of gamma is equal to, so remember I said that bulk unit weight is using the sample as is to do your computation. So they didn't say dry. So calculating that it may have water or it may not have water. So you are using the sample as a whole like that. And then expressing that further, you can use this formula from the chart or the table with the formulas. You derive this from there. And then you substitute all your parameters and punch, and you have this. So they are telling you that in case your soil is saturated, as in the case where we are dealing with, The one we are dealing with, they said our soil is saturated. So in this case, soil is saturated. So in this case, the soil is saturated. So the bulk unit weight is equal to the saturated unit weight. But then where your water is not such, your sample is not saturated, you are not going to have them to be the same. You can't say they are the same. You compute and get different values. Then they are asking us to calculate our dry unit weight. So we use this expression for that. So we pick the unit weight we computed from here over 1 plus W, and that will give us this. So the effective unit weight, what is it then? So effective unit weight is, because the sample is filled with water. The sample is filled with water. So we are assuming the water has got effect on the unit weight calculations we have done. So we want to find the actual weight, unit weight of the sample without it being saturated. So we want to take the influence of the saturation out of it, and that gives us the effective unit weight. So that one too, we have this expression. So you substitute this one here is the unit weight of water. This you have already seen that, and this is your void ratio. So substituting all of these parameters, you arrive at this parameter, and so you can easily get your effective unit weight. So now remember they said that where you have your sample being saturated, it is the same as the bulk unit weight you computed. So if you have computed your bulk unit weight, then it can be said to be the same as the saturated unit weight. And so your gamma sat. And then we have established some constants that the unit weight of water. So we want to take, remember I made mention that in this question, we are trying to take the effect of water from the unit weight. And so we already has established in our previous lessons that water has a unit weight of 9.81 kilonewtons per meter cube. So here if you know these constants and you know this principle that saturated and the bulk are the same because it is saturated, then you don't need to be looking or remembering this fancy formula. You can easily, or you could have easily decided to subtract the effect of water in terms of unit weight from the bulk unit weight you calculated, which is the same as saturated unit weight, and that will give you this answer. So now we want to look at soil states, the physical states of soil. So here, with the physical state of soil, the emphasis is that water has the tendency of affecting dramatically the strength and deformation of soils. It can change our sample to behave or cause it to behave differently. And so we need to know how water can influence our soil sample. And for that reason, we want to go ahead and know some of the behaviors or how soil is likely going to behave when it is under the influence of water. So under this physical state, we need to take note of some key terms like liquid limits. So it is the state at which water or soil changes from liquid state to a plastic state, which we will know these later on. And then we have the plastic limits, water content at which soil will transform from a plastic state to a semi-solid state. And in that order, so we get to what we call as the liquidity index. So let us see what these states are. So usually when I give a soil sample, a given soil sample to you, and you are asked to, we want to find out when water is added gradually, what will be the behavior of that soil sample when water is added. So now I give you a dry sample, which is this section. And as I keep adding water to it, then that soil sample will become semi-solid. Semi-solid in the sense that the water has been added to it. And so with the water added to it, it begins to behave as though, so this, look at the x-axis we have here. It is with increase in terms of water. And then this axis is showing us when the water is being added, the volume of the soil sample will also begin to increase. So as water is added, the soil sample begin to show some features, slight increase in volume. So with the increase in volume, with the addition of water, the soil will move from a solid state and then move to what we call the semi-solid state. And then here, what are some of the features or the things we can easily identify from it? We can easily see visible cracks appearing on the surface of our sample. That is when it is in the solid, semi-solid state. Then we have a state where we call the plastic state. So with the plastic state, you keep adding water and adding water till a point where it has increased in volume. Your water content or the content of water too has increased. But then at this point, deforms without visible cracks. So here you can mold your sample. So for example, if the soil sample is clay, you can easily mold it into various forms and shape without it showing any signs of cracks. And that is what we term as the plastic state. Then finally, you get to a point where you add water and then the sample becomes so watery that it begins to flow. It gives up. You can no longer mold it. You don't have control over how it's going to behave. It begins to flow. So when it is like that, we call that the liquid state. So here you see flows like any viscous fluid at all, depending on the quantity of the water you have added. And in the same way, as you begin to reduce the water content, and so this is the activity we do by putting the sample in the oven. We do that because we want to determine the solid state of the sample. And when we have the solid state, we can keep adding water to test the behavior of the soil under the influence of water. So then the boundary, so it's just like you pouring the water into the sample. So the boundary between the semi-solid state and then when the soil was solid, just before you enter into the solid, the semi-solid state, we term that as the shrinkage limit. The water you need just about getting your sample to behave as if it's a semi-solid sample is what we term as the shrinkage limit. Then when you get to the semi-solid state and you keep on with the addition of water, the boundary that distinguishes the plastic state and then the semi-solid state is what we term as the plastic state of the soil, just before your soil began to exhibit the behavior of plasticity. Then we have the liquid limit, the water you just are about to add or that will transform the limit at which your soil sample will be transformed into that viscous fluid is what you term as the liquid limit. That is the limit at which your soil sample will begin to behave as though it's liquid. So with these things, there are some stuff we can get from them. So we can compute what we call the plasticity index. Other people will write it IP. Some people will write it PI. Whichever one you want to use, there's no problem. Either this or plasticity index is equal to the liquid limit, okay? The liquid limit you have added, that is the liquid limit, the boundary of the liquid limit, this value here, whatever value of water you were about to add, or you are just about to add, that will convert your sample to the liquid state, is what we term as the liquid limit. So you have that percentage of water and you take away your plastic limit. The difference of that is what we term as the plasticity index of your soil sample. Then the next thing is you can compute what we call liquidity index. So when you look at the key words here, liquidity index, the ratio of the difference in water content. So you want to find, you've added water, so you are trying to find out the difference, the ratio of the water you have added to the sample between the natural or in-situ water content of a sample and its plastic limit to its plasticity index. So you are combining this parameter you computed from up there, then the plastic limit, and then which is it? And then your water content. And so when you have that, you have what we term as the liquidity index.